Okay, welcome everyone to this CDAC webinar. Today we're pleased to have Pinwin Guan from Carnegie Mellon, who will be giving us a talk. Pinwin is a computational material scientist who's worked on a variety of problems, focusing principally on computational thermodynamics. He received his bachelor's degree from Tsinghua University and then a PhD from Penn State in 2018, where he did first principles calculations related to photovoltaics. Since then, he moved to, has been at Carnegie Mellon, and there he's worked on a variety of problems, including electrochemistry and getting into deep learning, and most recently has been working with our group on the challenge of trying to stabilize the superhydride superconductors that we've discovered under pressure, but using a combination of electrochemistry and pressure. And today he's going to be telling us about some of that work, which is ongoing, as well as some of the other recent developments in his research program. So go right ahead.
Okay, thank you. So today I will talk about my two works on computational thermodynamics. One is more relevant to this series. It's about the electrochemical synthesis of superhydride under pressure. Another one is about the de-learning of thermodynamics. So I will start my presentation. So I will briefly talk about what is my research scope. So as you know, material science have many scales, and each scale will have the corresponding method to study. So my major focus is on the underlying two levels, which is phase, defects, and atom electron. And actually, I'm more focused on computational thermodynamics. So I will briefly talk about what is computational thermodynamics. Computational thermodynamics use data from calculations or experiments to construct a description of thermodynamic system, which usually in parameterized models, and we derive various physical properties based on this model. In material science, it can be used to obtain phase diagrams and parameters for simulations of phase transformations. And we have used a wide range of techniques in it, ranging from electron structural calculation to statistical mechanics models. So this is an example of application of computational thermodynamics. We apply it in calculate the phase diagrams of hydrides under pressure electrochemical conditions. As you all know, hydride have shown some superconductivity under certain conditions. So this is a list of the superhydrides where they are all binaries. Actually, people have studied all of the binary systems in the previous years. So you can see, although they have achieved quite high critical temperature, but usually the required pressure is very high. So it's often above 100 gigapascal. So it's a little bit challenging for application. So then we think, how can we relieve the condition and make it in more moderate conditions? So we generate the idea to combine the pressure and electrochemistry. You can see in this figure. So in this setup, we have electrolyte separate the anode and the cathode. The cathode is the anode is okay. The anode in anode the hydrogen will transport through the anode through the electrolyte and arrive the cathode. And the cathode is original a metal, and then you'll be you will absorb the hydrogen and become the metal hydride. And so in this setup, the reaction is actually the reactant is the metal and plus the hydrogen ion and electrons, and then we generate the metal hydrides. And you can see the Gibbs energy of this reaction can be written as a function of the electron potential and the hydrogen ion activity. So in this process, we should suppress the hydrogen evolution reaction kinetically. So in the interface, the hydrogen ion may recombine with the electron to form the hydrogen substance. So we want to kinetically suppress this, and this actually is a very extensively studied topic in electrochemistry. So we may leverage the knowledge in electrochemistry to solve this problem. So then actually in the hydrogen evolution reaction, usually there is an overpotential due to the intermediate state. So the whole reaction actually can be written into 2 steps. The first step is that the hydrogen ion will absorb on the surface or interface. And then this star represents a absorption site. And then this will generate a soft hydrogen ion on interface. And then two absorbed hydrogen atoms will combine into a hydrogen molecule. So you can see in this reaction diagram, actually there is a barrier in this reaction. So this is why there is a overpotential needed to overcome this barrier. And then people already calculate the overpotential for different systems. As you can see in this figure, the right figure, actually for different systems, the absorption energy actually correspond to kinetic barrier is quite different. For palladium, it's about, if you go to the Gibbs scale, it will about minus 0. Near minus 0.2 electron volts. So actually, the HER overpotential can be also tuned by electrolytes. So we can try different electrolyte to adjust this overpotential. So the next step is then we want to use some calculation to study in what condition the superhydride can be stabilized. So we construct a workflow for this purpose, and then we just because there is very scarce experimental data under high pressure. So we have to only rely on the calculations. So we start from DFT, and then here we actually want to use machine learning also, but in the preliminary work, we haven't tried this, but I think in the future we may try this because it will accelerate the calculation. So we use DFT to calculate the structure, which is predicted by some crystal structure prediction method. Here we use the capsule and with the method particle swarm optimization. So we calculated the energy of different structure, and we can and then for each structure we actually sample different volumes. Then we can generate EV calculation for different structure, and this will give us the Gibbs energy. So actually we didn't consider other corrections such as the harmony and unharmonic corrections. Here we just use the static energies. In principle, we should use Gibbs energy as a function of the structure, pressure, temperature, composition, and we do minimization of all of the structure, the energy of the structure we get. And so this will help us find out what structure is the most stable one. And then when we use this stable structure and their energy, we can construct the Pullback diagrams. This will be a function of pressure, temperature, potential, and pH. So this is the whole flow. And then for the binary system, we study palladium hydrogen. We get a structure from crystal structure prediction as these figures show the most stable one under different compositions and different pressures. So we can see under different composition, the structure is quite different. Actually, in the low hydrogen content, usually the structure is a compact structure, and if you increase the hydrogen content, then there will be more and more hydrogen molecules. And then we do a bomb topology of the analysis of this structure we obtain. So here, these 2 diagrams shows at different pressures how the coordination number and the dimensionality of the palladium framework will change as a function of the composition and pressure. So actually we can see here. So we can see actually in 0 gigapascal dimensionality is quite different for different composition. Actually, after the composition about palladium hydrogen 2, all of these dots show that these are 3D network, means that all of the palladium are connected with each other, although they may be some intermediate hydrogen as a bridge to connect these palladium atoms. But if we further increase the hydrogen content, then the dimensionality will decrease. So it can become 2-dimensional, and if we further increase the hydrogen content, it may become 1D. That means that we may just have some palladium chain there. And the coordination number also has changes. But at high pressure, 150 gigapascal, because the pressure is so high, so all of the palladium actually are interconnected with each other. So all of these, no matter what is the composition, they will be 3D network. And but also you can see the coordination will increase with the hydrogen content, because more and more hydrogen will be bonded to the center palladium atom. And then this figure shows the hydrogen distance of the structure. So you can see there will be the situation is quite different between the different pressures and also the compositions. The major change will mainly occur between the palladium hydrogen and palladium hydrogen 2, because you can see about composition of palladium hydrogen 2. After this composition, actually the distance will not change too much. But before this composition, there will be very drastic change of the hydrogen distance. So use this energy of different stable structures, we calculate the phase equilibrium of this system under pressure electrochemical conditions, and then we get this diagram. And then, so we found actually if we can combine these two conditions and suppress the HER, which is represented by this dashed line here, and then it's possible to stabilize palladium superhydride at more these conditions, about hundreds of megapascal. No measure. It's millions of Pascal. Yeah. So, and we also study other binary systems, which show here. We find actually this is a general method to stabilize the superhydrides. But here we show the HER line is just based on the absorption calculation on the metal surface, which does not account the variable hydrogen content, because when you hydrogenate the metal, the hydrogen content will change, and this will change the absorption energy. So we haven't considered this effect in the calculation. So this may push this HI line even to more positive potential. And then this is a ternary system we study and have not published yet. So for ternary system, the situation is more complicated, because now you have 2 degrees of freedom in the composition. So if you change the magnesium-lithium ratio, the phase equilibrium will be different. Here we just show the magnesium-lithium ratio between 0 and 0.25. So in this range, and we can see there will be actually many different regions, and usually the phase will be two-phase. The region will be 2 phases coexistent. So this is much more complicated than binary cases. And actually, we find if we don't apply, we apply zero potential, then there will be no ternary hydrides exist. This is consistent with the previous work about this system. But if we apply some negative potential, then we have the possibility to stabilize the combination of a binary hydride and a ternary hydride. So this is the work. The previous is about the work about the electrochemical phase diagram of superhydride system. So next topic I will talk about how we can use the deep learning to machine learn the thermodynamics of materials. So the first point to talk is that materials is a complex system. So there are a lot of variables here. You can change the composition, temperature, pressure, field, such as electric field, like we do in the previous study, and also the magnetic field. And you also can change the string, can change the size, and all of these factors will influence the performance. And actually, this is a simple error here, but it actually have a lot of intermediate steps. For example, if we have 100 elements in design space, then you have so many different systems. If you go to 4-element system quaternaries, then you have more than 3 million different combinations, and this does not count. You vary the ratio of different elements in your system. So if you account that, then you have much more numbers. Another feature is that it's a multi-scale. So you study from the electron atom to phase defect up to microstructure. And then the coupling between scales involves sophisticated simulations. For example, in thermodynamics, actually, if you want to get the phase equivalent from the Gibbs energy, then you need to do thermodynamic calculation. This is a kind of simulation. Also, this because of this feature in multi-scale, so you have heterogeneous data, because in each scale you will have different types of data. Because you have multi-scale, so you have data in different levels. So this is very homogeneous. And for such a complex system, usually we use the trial and error method, which we usually do this in material science. Also heuristics. So for thermodynamics, the heterogeneous data is actually can have this kind of forms. We have 2 types of data. The first type is thermochemical data. It consists of free energy, enthalpy, entropy, heat capacity, activity, and some others. And for phase equivalent, we mainly have the phase boundary. For example, here we show the titanium hydrogen system. You can see actually that you will have some solid solution in the 2 mm side, and then you have some intermediate compound in the middle. But intermediate compound usually also have some solubility. So actually, this you can see different phase boundary here. This is a kind of data. So these 2 types of data are quite different, but they are coupled actually. So how can we? The question is how can a machine learning method learn both of them? Also, another problem is that in the machine learning, we usually want to incorporate more phases, because this will help us to generalize the model better. So how do we integrate? We have two approaches. The first approach that we use simulation to generate some data. So this data contains some physics, and this data will train the machine learning model. But this is not as better as the second type, I think. The second type is that we have the data, and in the machine architecture, we already incorporate some simulation in the machine learning architecture. So it will be, so this type will be more data efficient and more accurate. And then we want to you develop a machine learning method to learn the thermodynamic data. So we first observe the features of deep learning. So in the deep learning, as you know, it's a series of layers of networks. So you have input, and then you go through different multiple layers. Then you have the output. So and then how do you train this neural network? You actually calculate a gradient and use this gradient to optimize the loss function, and this loss will backprogrammed towards the parameters, and then you can adjust the parameter to train the model. So how do we calculate the gradient? We use the chain rule backpropagation. So the question here is that do the component need to be linear function plus the activation function? So the answer is no. So a guy in the machine learning community said his opinion is actually this is a mix of English and French, I guess. But his meaning is that we should use a more general point of view about the deep learning. That is, we shouldn't limit it to the deep learning. We should extend it to differentiable programming. So another physicist said, a physicist called Richard Feynman said, what I cannot create, I do not understand. So the meaning is that if we can So usually, if you have done some results, if you can reproduce them by calculation, that means that you understand it quite well. Otherwise, you haven't understand it quite well. So, but I think we shouldn't stay in this level. We should say, okay, what I cannot differentiate, I do not learn, because we don't just want to get a result under particular conditions. We want to know if we vary the condition, how the result will change. So this is actually the deep learning can do. But for deep learning, we need to make our model differentiable. So this is so we also have some learning from the Nobel Prize. So the last year, the physics prize given to 3 people, and actually their field is quite different. So 2 people, they are focused on climate modeling, and the third one focus on the statistical mechanics, and it's more close to material science. But we say actually a similarity between climate modeling and material science is that actually they both study high-dimensional multi-scale complex systems. So actually, in fact, the earliest field recognizing importance of differentiable programming is climate modeling. So so have these ideas in mind. So I developed a differentiable thermodynamic modeling. So here you can see we can learn both types of data, thermochemical data and basic equivalent data. How we can do that? Because we actually may transfer the whole thermodynamic modeling into a differentiable framework. So the whole framework can be differentiated. So you can differentiate the loss function with respect to the input parameters. Then you can train the model in a deep learning style. So, but actually, you are also doing thermodynamic modeling. So they actually this way will combine thermodynamic modeling and deep learning into one. And then this is a simple case applied in copper rhodium system, and you can see here we trained our model, and the loss function will decrease and then finally close to 0 with training goes on, and then you can see the loss gradient also approaches 0. And the model parameter will approach the true value. And actually, we restore although we start from a very unreasonable initial parameter set. That means you can see the Gibbs energy. The deeper the color, so the initial result represents the light color. So the light color we have a convex function, which will not result in the phase separation behavior. But if we train the model, we can see the Gibbs energy function will become non-convex. This will give a miscibility gap, as shown in this figure. So actually, in the low temperature, the FCC phase will have to actually, in the intermediate range of composition, it will separate to 2 phases, FCC1, FCC2. So actually, if the training goes on, we can see this behavior appears in the Gibbs energy. So I have implemented this in a demo code, so which is online. And this is written by JAX and is a differentiable programming language. So use this training data, we have trained the thermodynamic model of this system, and the result, the calculated phase rise is in agreement. I think this is a very simple system. It's just a binary, but if we can apply it to a high component multi-component system, I think the principle is the same. So then at that time we can use some machine learning features to learn the phase stability. Thank you.
Okay, very much. Are there questions or comments for Pinwin? Just use the chat or raise your hand. On the last part, what were the parameters or the features that you were training on, and how many are there in those calculations?
You mean the training data?
Yeah, right.
Okay, the training data is just this phase boundary. So you can see the red dot here.
Okay, but in the previous, what were the parameters that you're looking at the gradients of?
The parameter is the parameter in the Gibbs energy of different phases. So, for example, in the FCC phase, we actually can expand its missing enthalpy into a RK series. We have a regular parameter, subregular parameter, and we train this parameter in the Gibbs energy.
I see. Okay. Okay, Bryce, go ahead.
Yeah, could you go to the slide at the beginning where you showed the electrochemical synthesis of the metal hydride?
Yeah. You mean this?
The one where you were showing the anode and
Okay. Setup. Okay.
So what so if I understand that the type of Courbet, or let's say pressure electrochemical diagram, you would both need an elevated pressure and a potential to synthesize the metal hydride. Is that what you're thinking, that you would do this? You would do this, but at a high pressure?
I think we want to make the pressure as moderate as possible, but if that depends on how we can optimize our other conditions. So this is the result of the multi condition. So we can change the temperature, pressure, and also the composition of our system. So maybe for this composition, we need to have very high pressure, but maybe we change some other composition, the pressure can be made much lower. So this is a optimization of different conditions together.
Yeah, I guess I would just be worried. I mean, not all electrochemistry is done in water, but a large amount is, and that if you were to, and you normally need some salt in the solution to make the solution ionically conductive, and that you would be drastically changing the structure of the water in the salt solution depending on the pressure that you're at. So it would just be something to consider in terms of the practicality of how the structure of the salt solution changes at the pressure where you want to synthesize the material.
So I think I guess you talk about the water refers to an electrolyte part.
Maybe there's some other electrolyte. Yeah, that's a possibility. You could use an ionic liquid or something, and maybe you could get around that.
Then we may use some solid electrolyte. Solid electrolyte will be more resistant to the pressure change, I think. Yeah.
Thanks.
Yeah, but you're absolutely right. You will need to study the pressure properties of the electrolyte to make this work. But the idea is to do it at as low as pressure as possible. Okay,
yeah, this is a good question. I think there are a lot of technical details related to the experimental side, actually. How we choose the electrolyte, how we choose other setting. This is important, I think.
Thanks.
Okay, Sabri?
Yes, I have a question on the last slide. I don't know, I didn't understand what's the difference between liquid plus FCC and liquid state, and how you can distinguish between them.
Okay, so your question is that
liquid plus FCC and liquid. So how you, in simulation, actually, how are you gonna distinguish between them? Like, and how, what's this one? What's the difference between them?
The difference that the difference that in the intermediate region, if you observe the phase combination, you will find a liquid and FCC coexisting. But if you go to a pure liquid side, you just have the pure liquid. So these are all from the experimental observations. But if you really have very accurate first principle calculation, can generate this phase sequence, that is also possible. But usually we observe this data from experiment. Yeah, in experiment they will measure the invariant reaction. So usually in this phase bond there will be some quantity which will be in the they will keep fixed because they are in the timeline actually.
Okay, thank you.
Yeah.
Okay, Lei has a question. Would you like to ask it?
Yes. Correct me if I'm wrong. So you utilize the electric potential to assist the hydride synthesis, which typically pressure does the work. So I'm wondering, since the electric potential is typically occur only at the interface, so it more acts on the shifted energy level of the hydrogen or proton and the electron part, but not the metal part. So how the metal, for example, in a superhydride form, the metal sublattice will reconstruct or totally reform, recrash and reform another sublattice structure. So how electric field could do that comparing with the pressure, the pressure typically will do the work. I'm just curious about that.
I think the electric field probably don't have a very large effect on the metal lattice. I don't mean they don't have effect. I mean the direct effect is not very large, because if you have the for hydrogen ion in the electrolyte, you can have the potential will change its energy or activity. But no, I think the, so here is that actually we consider the electron and hydrogen ion as a system. So the potential will change the energy of the electron. So it will change the relative stability between the system consists of electron plus hydrogen ion and the hydrides. So this is the core idea. But for metal lattice, I don't think there is a direct effect on it, because it does not have a charge there, so it's neutral. Yeah, I think the change is more on the hydrogen side. So the hydrogen will have higher energy, so it will change the structure of metal, but it's not, so it's a not direct effect.
Yeah, I'm just wondering the so the superhydride typically has a very different metal sublattice compared with the pure metal itself, right? So yeah. I just suspect there is a huge kinetic barrier out there.
Right.
That typically pressure can do the work, but I'm wondering if the electric field can really do the work. I mean, thermodynamically, it will shift the lattice stability between the reactants and the products, but how it could overcome this kinetic barrier by the electric field, I just a little bit suspect.
Yeah, I haven't considered kinetic effect in these diagrams. All these are thermodynamics. So yeah, right. Actually, there will be, because you change the type of the metal lattice, there will involve the breaking of the metallic bonds there. So I think this will have some kinetic barrier there. So I think actually in practice, I think either you increase the temperature will help you overcome the barrier. So another is that maybe in the practical products, yeah, it's not like equivalence phases. Actually, some metastable, but the kinetic barrier is smaller. For example, some people have do experiment to synthesize the palladium 3 hydrogen 4. Actually, in our calculation, this phase is not thermodynamically stable one. It's metastable. So I think it's possible, because actually it's the point is that actually this phase, it has a FCC metal lattice. It's the same with the pure palladium lattice. So that means that the kinetic barrier is small. So finally they get this phase with smaller kinetic barrier. So but that means that at the same time their thermodynamic stability will be weakened. So maybe the phase boundary will be towards more negative potential side.
Okay, thank you.
Yeah.
That question does bring up the interesting broader question of just the effect of the electric field plus the pressure on phase boundaries when you have a dielectric. The normal state could be dielectric, and you could be stabilizing different states just due to the electric field, shifting phase boundaries.
Sorry, you are talking about the in the chat channel?
In general, I'm just talking about in general, just the effect of electric field on phase boundaries. If you have a dielectric that can be polarized, for example,
Oh, okay, okay.
say stabilizing a ferroelectric state in a field.
Yeah. The polarization induced by electric field.
Right.
Yeah. There will be this kind of effects. We haven't considered this yet. Yeah, we haven't considered many other factors actually. Yeah, for example, the harmonic and harmonic contribution to the Gibbs energy. We haven't considered this yet. Yeah, but I think this will be interesting to consider in the future.
Okay, thanks for the question. More questions or comments? Okay, well, the challenge now is for experimentalists to realize this prediction, right? Okay, well, thank you very much, Pinwin.
Yeah,
Very
thank
nice
you.
talk. Thank you all for joining us.